Well, thank you. Welcome to the LPI. I'd like to just say that I've been working here for 24 years, and it's a fantastic place to work, and I hope that you can come back and visit the library. We've got a fantastic library. And let's get started. What I want to do today is to give you a preview of coming attractions. Basically, it's like, think of it as going to the movie theater, seeing the previews, and then the movie projector goes out. And you have to come back a couple months later to actually see the movie. Although I do have a couple of pictures I will show. That's because there's as Andy mentioned, there's a lot of interesting things coming up this year in planetary exploration. I want to talk about that. Basically, I want to talk about what are dwarf planets, and then I'm going to talk a little bit about Ceres and what the mission profile is going to look like for that, and then the encounter with Pluto in July, and then we're going to have hopefully a lot of time for question and answers, and then some free food out in the lobby. Free food, yeah, that's why you're all here. I always like to start with this slide because it's basically the cover of this book. And some of you may actually remember this book. It's one of those children's series that they had in those days. And I read this as a kid, and I learned all about the planets. And there wasn't much to learn in those days. Basically, everything that we knew could actually fit in a book this size. But this was in 1960 at the dawn of the space age. We hadn't really even seen the backside of the moon except for one picture, and we had no pictures of Mars that were worth noting. And you basically had 9 planets. You had one ring system, which is the famous ring system of Saturn, and a few stray comets, but not a lot was happening. It wasn't a very dynamic and interesting place, at least so we thought. Flash forward to 2015, and you have 5 zones, and I'm going to talk about that in the next slide. 8 planets. Comets hit planets all the time now. You have rings around all 4 of the gas giant planets. You even have evidence for rings around several of the moons of the giant planets, although they're not there anymore. They were in the past. Volcanoes spewing vapor off of the surface of icy moons. And that's just a short list. There's lots more interesting things going on. But finally, there's also the dwarf planets, and that's the subject of what I want to talk about today. Now, I mentioned 5 zones. Typically, when we say the solar system, you think of the inner planets, the rocky inner planets. We're on one of them. There's Mars, Venus, Earth, that sort of thing, Mercury. And then you think of the giant outer planets, Jupiter, Saturn, Uranus, and Neptune. But it's actually more complicated than that. There is the inner planets, which on this diagram is so small you can't actually see it. It's that little gray dot in the center. Then you've got the asteroid belt, which is the bright orange donut-shaped thing in near the center. And then, of course, the 4 giant planets. And then you have the Kuiper belt. And the Kuiper belt is actually this belt of small objects orbiting just beyond the orbit of Neptune, out forming another donut, if you will. And then way out beyond that, way up over the ceiling and under the floor, orbiting around, is another cloud of material. It's called the Oort cloud, and that's where the comets come from. But we're going to focus on the asteroid belt and the Kuiper belt, those 2 zones of debris, if you will, that form in the various parts of the solar system. And the dwarf planets are in those 2 zones, the asteroid belt and the Kuiper belt. And I'm not going to talk about the Oort cloud because we haven't actually observed anything out there yet. They're too far away. Pluto and Ceres are the largest of these objects in their respective zones. Ceres in the asteroid belt here in the inner zone, in the inner part of the solar system, and then in the Kuiper belt, Pluto is the largest representative there. These bodies are large enough to be considered planetary in nature, and I'm not going to get into the argument over what's a planet here. I don't really want to get into semantics here. But by planetary, I mean that they're large enough to be spherical. Some of them have moons. As we'll see, Pluto has moons. But they share their zone with objects of similar size and character. Jupiter and Saturn really dominate their respective orbits. There's nothing else to compete with them. These objects, these dwarf planets, are probably leftovers from the formation of the planets themselves, and that's why they're important. These are some of them. These are the largest ones anyway. I show the moon and the Earth for scale. Ceres is the largest asteroid, and it's the one we'll be talking about first. Then you have Pluto and its moon Charon. These are all shown to scale. And then these 2 objects are also Kuiper belt objects, and they share the zone with Pluto. And they're of comparable size. Everything else is smaller than these. in their belts. So let's step back again in time to January 1st, 1801. There were 7 known planets. In fact, Uranus had only been discovered about 15 years before that time. And astronomers didn't have a lot to talk about when it came to the planets, so they talked about spacing and issues like that. So they noticed that there was something of a gap here between Mars and Jupiter, and they wondered, well, maybe there was something there. So astronomers started looking. And actually, by accident, Giuseppe Piazzi in Palermo, Sicily, on January 1st, it's quite a way to start the millennium, discovered a small planet between Mars and Jupiter following this orbital path, and it seemed to actually fit the bill. It filled the gap, if you will. But as it turns out, and it was named Ceres after the goddess of agriculture, but there were a lot more that were discovered slowly at first. By the end of the 1800s, there were about a couple dozen of these objects. But as telescopes grew in power, the discovery rate magnified rapidly, and by the present epoch, we have over 500,000 such objects that have been cataloged. And they became known as the vermin of the sky. Now, what does that mean? In those days, they were considered basically rocks in space, and a lot of people still consider them rocks in space. And they tended to get in the way. In those days, if you wanted to take a great picture of the Orion Nebula, you had to make a long exposure, and then, bam, some damn asteroid would come across the field of view and ruin the shot, and you'd have to do it again. And nobody really wanted to study them, except for those people who were interested in the drudgery of measuring their brightnesses every day and seeing how they varied. And it's like, well, there weren't too many people interested in that. So they became the vermin of the sky. Nobody really cared about them and was interested in them. But they are of some interest. One of the reasons is that asteroids come in many shapes and sizes and compositions. But the most important thing is that we have samples from the asteroids. And those are the meteorites. And you can see a variety of them here. It really doesn't matter what they are. But some of them have like olivine. This one has olivine and iron. And there's some stony ones. And some of them are carbon-rich, carbonaceous chondrites, for those of you who know. All of these are relics of planetary formation, and some of them have been knocked off asteroids. For example, Vesta, which I'll talk about briefly if we have time, was the first target of the Dawn mission, and the HED meteorites came directly from a large impact on the south pole of that planet, the planetary body. So if we can go to the asteroids and understand their geology and their history, and correlate them with the meteorites, then we've got a big window into the history of the solar system. Now, to get a sense of scale before we go on, Ceres is this little guy here. And this shows some of the inner planets to scale. You recognize Mars, of course, I hope. That's Mercury from the new messenger data that we've been accumulating since the spacecraft went into orbit a couple years ago. That's the Moon, of course. Then Ceres. Down there is little Vesta, which I just mentioned. Ceres is only about 1,000 kilometers across and would fit inside the borders of Texas. So it's a little guy, but it is the largest of the asteroids. It contains 1/3 of the mass of all the objects that we have currently in the asteroid belt. That's a large percentage. So it's a pretty important body to understand. As I said, indicated, the asteroids languished, and Ceres is among them, languished in obscurity for a couple hundred years. No one was really terribly interested in them. But we do know a couple things about it before we arrive this year, and that is the size and the mass have been roughly well determined. It's found that Ceres is probably about half water ice. That's pretty significant. Clays and carbonates are the only things that have been identified in the surface, but we really have very low resolution. Clays are important because they contain water. They're a mixture of silicate and water and indicate alteration of the rock. At least here on Earth, that's what they would indicate. On Ceres, it's another matter. But this is the best image that we've ever had from the Earth, and it's the HST Hubble Space Telescope image. And you can see that we really don't have a very good handle on what's going on, at least from the Earth. Now, what do we think is going on inside Ceres? Well, this is probably a fair representation. And we'll know from the mission, from what the interior structure is actually like. There's a rocky inner core, probably. There's an outer layer of water ice. And then there's a thin outer crust of dark material. The surface of Ceres is actually much darker than actually a little bit darker than the moon. Now we think of the moon as being bright because it's in the contrast of the dark sky and it really shines brightly at night, but it's not. It's actually a fairly dark object. Has an albedo of about 10%, so it reflects only about 10% of the light coming in. And Ceres is even darker. But we know that there's water ice from the low density of the body. So, but it is covered with this dark material, the clay and the carbonates that I mentioned earlier. Now, it's also possible that this rock and ice might be mixed in a sort of homogeneous mix, but this is what we think is probably going on. And some of you probably have heard that 1 or 2 years ago, orbiting telescopes, orbiting around Earth that is, observed water vapor around Ceres at particular times. Not constantly, but at particular times. It was not something that's ongoing all the time. It's some sort of episodic thing. But of course, the resolution was very low. We don't know what the source was. We don't know whether it was volcanic or just some impact spewed it out and blew stuff into deep space. We don't know. So there's a question. Is Ceres some sort of active body, like some volcano spewing out stuff? We don't really know. That's one major reason for wanting to go there, of course, is to find out. So, finally, in 2001, the Dawn mission is approved to visit 2 of the largest asteroids, Vesta and Ceres. And I'm not going to talk much about Vesta here. But this is the launch appropriately at dawn in September. I can't remember the date exactly, 2007. And is the first mission to visit the largest asteroids. Dawn carries a stereo camera, which is useful for measuring the topography of the surface. It carries an infrared spectrometer, which is important for measuring the mineral composition, what the minerals are on the surface at high resolution, so we can correlate the geology with the mineralogy. Gamma ray telescope is useful for measuring the elemental composition. What's the abundance of hydrogen and calcium and magnesium, the stuff that makes up the minerals, that sort of thing. And there's also a gravity mapper, which is in the form of the radio antenna. We measure the Doppler signal, and we measure the gravitational perturbations as the spacecraft goes around. And that's going to be key for understanding the interior, because that'll tell us what the mass distribution is inside the body. And of course, we don't have that yet because we're not in orbit. Now, I seem to have what Andy has. Dawn also carries a solar-powered xenon ion engine. Now, what the heck is that? You know, I'm not an engineer. I'm a geologist, damn it. So I don't really, I really can't explain it very well. But what it does is it takes xenon gas and ionizes it and then expels it out the backside. This is not a very powerful engine. It's got about thrust equivalent to the weight of a paperclip, which is, you know, not the Saturn V, obviously, or a Delta, or any of those things. But the fact is that it's almost always on. It's constantly thrusting, expelling energy, gently pushing the spacecraft. It's like wind in the sails of a sailboat. You know, even a light wind will get you eventually to Bermuda. And this shows the flight path of Dawn. And you can trace its orbit in blue. The areas where it's light blue is where the ion thrusting was on. And you follow it around, had a Mars gravity assist. Then it went out, eventually reaching Vesta, where it spent the better part of a year mapping at high resolution the surface of that body. And then it left Vesta, and for the past 2 years has been slowly coasting until it reaches Ceres right down here. And Ceres' arrival is scheduled for about 1 week from now. Now, by arrival, I mean gravitational capture, when basically we can no longer escape the gravitational pull of the body. Easily, anyway. So this is it. This is the picture that was released yesterday, or the day before, I forget which. And this is the best view we have of Ceres, obtained by the spacecraft on approach. It's now, I forget what the distance is. It's about 30,000 kilometers from the surface. That's well inside the orbit of the Earth's moon compared to the surface of the Earth. So it's really quite close now. The smallest features that we can resolve are about 4 kilometers across. And who remembers the conversion to miles? That's about 2 miles. 2.5. 2.5 miles across. That's about right. Which is which is okay, but we're going to get much better, and I'll show you some examples of what kind of resolution we're going to get in a few minutes. But it's enough to get a sense of the lay of the land. And I don't want to belabor this image too much. I'm going to save it for later for the discussion period, okay? But I'm going to mention a couple of things that have caught people's attention. Remember, this body is about the size of Texas, so keep that in mind. There's obviously craters with central peaks and other things. It's a fairly heavily cratered. It looks a lot like the satellites of Saturn. And I'll have a picture of that in a few minutes. Satellites of Saturn are also icy in composition, and they're actually of similar size. So they'll make a good comparison when we get the high resolution mapping. Now, there's a couple other interesting features. This is a circular feature here, which is about 250 kilometers across. And it's obviously an impact basin, but it's very flat. Something's modified it. At this resolution, we can't be sure whether it's creep of ice, and at warm temperatures, ice will flow like glaciers on the Earth, and the terrain will soften. But some of it actually looks like it could be some sort of volcanic infilling, lava flows. And the team the science team is debating that, but we really don't have the information. We need the high resolution to actually determine what the origin of that sort of deposit is. You can see it's really quite smooth. Something has clearly happened in this area. It means what that really means is that Ceres has not been dead for 4 billion years. It's something interesting has been going on here. Now, obviously, this bright spot is what's attracted a lot of attention on the internet, the forums, on manned spaceflight, for example. People have been trying to figure what this is since Dawn started imaging and found it. I think it's actually been visible in Hubble, the Hubble image, I think, as well. But there's actually 2 of them, and they're at the bottom of this crater. And this crater is fairly recently formed. There's some dark material on one side of it. We actually don't resolve it. It's just a couple pixels across. We don't know what that bright material is. It's got an albedo much brighter than anything else, about 50% or so, which gets you into the ice range. So it's probably some sort of fresh exposure of water ice. But whether it's a small impact that hit this area, or whether it's some sort of geyser or fumarole or vent, is a bit of a mystery, and one of the things we're going to look at. And of course, there's all sorts of arcuate things all over the place. It's quite a fascinating place. So that's the teaser. That's the fun new stuff. And before I get into what's coming up, this gives us again a sense of scale. This is one of the new images, and this just shows all the other asteroids that we've visited with spacecraft to date. Vesta is the one that Dawn looked at in 2011. Mapped at very high resolution. That shows it, and then a couple other asteroids. You can see there's not very many that we've looked at, but we have a pretty good idea what asteroids look like now. But this gives us a sense of scale and relative appearance. So what's coming up? Sorry. This is from Eyes on the Solar System, which you can download from the internet. It shows where all the spacecraft that NASA is operating are, even the European spacecraft, the Rosetta spacecraft. You can track that, which is orbiting the comet right now. And this was, I actually captured this a couple days ago, so it's actually moved a little bit up on the trajectory. This shows the approach of Dawn to Ceres and how it's going to enter orbit, which is what the process the spacecraft is doing right now. It actually does a little bit of a hook over the top. The North Pole goes out a little bit and then comes back in and then finally enters a polar orbit. There it just keeps going around and around and around. So we're about here, right about the top of the crest now. And over the next month or so, it'll take about a month for it to get into this orbit here. Capture happens right around here somewhere, where the gravitational attraction of Ceres is powerful enough to keep us in orbit. These are the mapping orbits that we're going to do. We're actually currently now somewhere up here, just outside the bounds of the room. These are the 4 mapping orbits we're going to do. We're going to do a short orbit here in April, and then we're going to do a long orbit here in June. We'll have, in the April orbit, we'll have resolutions of about 1 kilometer or so. Eventually, on the last orbit, we'll get near global mapping at about 35 meters or so. which is better than anything we have in the Saturn system from Cassini, for those of you who know. Now, we don't just jump from orbit to orbit. Because of the ion thrusting, we actually take a very slow spiral in, and that's what this diagram does. It's kind of psychedelic, but it does show the slow, steady progress. That's why it takes so long between April and June and then August to get into these orbits, because the ion thrusting is very slow. So just a preview of the sorts of resolutions we're going to be getting. This is images from the Saturn system, which is what I've been spending a lot of time mapping on. This is icy moon Dione, which is almost exactly the same size as Ceres, by the way. Also very rich in icy composition. It won't look like this, but it'll look similar. This is just to give you a preview of the sorts of resolutions we're going to see and what kind of things we can measure. This is I think this is the second orbit series that we're going to get. You can see ridges and scarps and valleys and lots of details in the impact craters. I'm not sure we'll see this on Ceres, of course. And then at the highest resolution, this is what it's going to look like. It's going to be really fantastic. Pardon me? That orbit is about 400 kilometers above the surface. Yeah, I think it's above the surface, yeah. So it's really going to be very close, yeah. And that's actually going to be the final orbit. That's the fate of Dawn, is to stay in that orbit until it runs out of power. So we're not going anyplace else. Okay, so that's where we are. Again, we're coming in like this, dropping in, and we're going to just end up in orbit. Mapping like crazy. And it's going to take most of the year to finish that job. The last orbit starts in November, and that continues for a couple months. So we're going to be seeing Ceres images throughout the year. And this is just a nod to the dozens of people who work at JPL to make this mission possible. This is the command center at JPL, and there's another one at APL, which is in Baltimore, that runs the New Horizons mission. And that's the next topic, Pluto. Now, obviously, I don't have any pictures to show you because we haven't gotten there yet. Actually, I got one picture at the end, but you won't be very impressed. Sorry. You can ask Andy for your money back. This is the New Horizons spacecraft in an artistic rendition of what some people think Pluto might look like. And we'll talk a lot about what's on board the spacecraft in a moment or two. Just a reminder, of course, many of you know, Clyde Tombaugh discovered Pluto at Flagstaff. He didn't discover Pluto was at Flagstaff. He was at Flagstaff when he discovered it. Stating the obvious. That's Clyde there, and these are the discovery plates. This is January 1930, just after the stock market crash. I don't think they're two are related, but anyway. And there's a story behind that, which many of you know, that there was evidence of gravitational perturbations of Uranus and Neptune. People kept thinking there was a large planet out there, and it turns out those measurements weren't very accurate, but they still looked anyway. They didn't know that. Searching for the mysterious 10th planet, Planet X. And eventually they were bound to discover something because there's a lot of stuff out there. It's called the Kuiper belt, all these small things. We didn't know very much about Pluto. It took a long time for us to get reliable measurements. It took a long time for us. In fact, I just remembered there's a fantastic plot that somebody showed that the estimated diameter of Pluto actually decreased over time at such a rate that in around the year 1988, it was supposed to disappear. And that theory was incorrect. But anyway, it was a very funny article. I have to dig that up again. But anyway, I digress. We do know from the infrared spectrum, and for those of you who aren't familiar, this is basically a measurement of the brightness at different wavelengths, and this is the infrared spectrum, which is basically the heat, where you feel it as heat, basically. You don't see it because our eyes aren't sensitive to it. But you measure the brightness variations, and you can actually identify species. In this case, this is carbon monoxide, which is poisonous, and there's methane, which is natural gas, of course, and there's nitrogen, which is what we breathe in the air. But the surface is so bitterly cold, about 30 to 50 degrees absolute, or minus 200 something Fahrenheit, that those species are actually frozen on the surface. The natural gas and the nitrogen are frozen on the surface as frost. Then the large moon Charon, which we know not much about, which has water, ice, and ammonia on its surface, was discovered in 1978. And 4 more moons, very small moons, have been discovered in the past few years. So the system is actually quite complicated, and it's very planetary in nature. This gives a sense of the size and scale of these bodies. Again, this is Ceres, Dione, which is the moon I showed you just a little while ago, and Celadus. Some of you will remember Enceladus. That's the one with the active eruptions at the South Pole coming off the bottom. Of course, there's the moon for scale. Pluto is actually quite large in comparison to these bodies. It's a little bit smaller than our moon. And Charon is actually close in size to the Saturn satellites Dione again. So Pluto is going to be a larger body to work with as we map it. What do we think the inside of Pluto looks like? Well, pretty much the same sort of story we saw at Ceres. Rocky core, and the thick icy mantle, and then frozen ices on the surface. We don't know how thick they are, but there could be a thick outer rind of methane and nitrogen of some thickness on the outside. And it's clear that Pluto has more of those ices than Ceres does because it's so much further out. They're more stable. If we had methane and nitrogen on the surface of Ceres, it would boil off, basically. It's too warm. Surface of Ceres is about 250 degrees at noon, which is pretty close to the melting point of ice, actually. Pluto also has a thin nitrogen atmosphere with a little bit of methane mixed in. And this is actually very similar to the case that we saw on Triton. Triton is the largest moon of Neptune. And this is an image of Triton. It is not Pluto. But it does show on the limb here this thin layer of haze detached above the surface. Basically, it's like a fog bank high in the atmosphere, about 10 kilometers above the surface. And Triton also has erupting geysers, and this dark streak right here is actually a deposit from one of those. There's a vent. There's about 5 vents on the surface that are erupting nitrogen gas into the atmosphere, and the wind actually blows it, and you can see the streaks on the surface. It's quite fascinating. And that's one of them right there. The atmosphere is very thin, though. It's more like the atmosphere of Mars, like a thousandth of the atmospheric pressure that we have. You would not be able to breathe it even if there was oxygen there. It's just way too thin. We don't know what the surface of Pluto looks like. We have in fact, that's basically the Hubble Space Telescope view of Pluto. It's just so far away, about 30 astronomical units, that this is as good as Hubble can get. So we haven't even matched that yet on our approach. But we know what icy satellites look like, and this is a montage of views from the Saturn system. This is the Herschel Death Star crater on Mimas. This is the equatorial ridge on Iapetus. These are fractures on Rhea. And these are impact craters and smooth plains on Dione. So, these are examples of what we might possibly see in the Pluto system, but we don't really know, of course. Pluto, of course, has friends. For 60 years, we thought Pluto was a lone outcast orbiting out beyond Neptune all by itself. But, of course, starting in 1992, when the first of these objects were discovered, and there are several thousand now, we found that there's a whole cast of characters out here orbiting with Pluto out just beyond the orbit of Neptune. And it probably extends quite a bit further, but our astronomical sensitivity isn't strong enough to get us out to those small objects yet. Pluto has a twin, and that happens to be Triton. I mentioned Triton. We just saw an image of Triton. Triton is, again, the largest moon of Neptune, and it is believed, and there's good evidence for this, that Triton used to be in the Kuiper belt in the same zone as Pluto, but it wandered too close to Neptune and got captured. And that had a devastating effect on it. And let's see, we've got a movie here. There it is. This is a movie of... I have to press the button again. There it is. This is a movie showing the Voyager 2 encounter with Triton back in 1989. And I was privileged enough to actually be there at the time to watch this. This is not the actual movie. This is sort of assembled from the map that we made. And it shows the pass over the North Pole of Triton. And you can see it's a very complicated surface. Those are some of those eruptions, those geysers over here. You see this weird terrain, which nobody really understands, and this volcanic terrain here, which has been resurfaced. And there's some more resurfaced areas there, impact craters. This movie is nice to watch, but it also gives you a little bit of a sense for what the encounter is going to be like when we reach Pluto. It's very similar in geometry, very high speed pass going straight through the system, right over the top. We'll look around, we'll pan back, and we'll see the crescent as we disappear. So it's very similar in a sense. It gives you a visualization, if you will, of what the New Horizons encounter is going to be like in July 14th. So getting on to New Horizons and what we're going to do and see there, selected in 2000, it was launched in January 2006. It's the only launch I've ever personally witnessed, and it was the fastest launch ever. We passed the moon's orbit in 9 hours. Just think about that, 9 hours. That's fast. It took Apollo 3 days to get there, but they were on a leisurely tour, 3-day tour. So, where are we now? This is the flight path. Again, high speed, straight shot with a brief detour at Jupiter. We got a gravitational assist. It saved us 2 years of travel time, the slingshot, basically. Now, the odd thing is that it actually slowed Jupiter down, so that in about 2 million years, it'll be 1 centimeter short of where it would have been if New Horizons hadn't been there. Oh, the damage we're doing out in the solar system, I mean, really. That's just unbelievable. Anyway, so this is where we are right now. You can follow it on the New Horizons website, which just Google that. I don't have it here. And as you can imagine, we're all eager to get there, so it's chomping at the bit. We want to get there as soon as we can. This is a spacecraft. It's about the size of a grand piano. So remember your grand piano from your lounge lizard days. That's about what the size of it is. These are the basic instruments. Again, Rex is the radio signs. That's how we track it and get the data back, and also how we get the gravitational influence of the body so we can measure its mass more precisely. Pepsi and SWAMP are 2 particle instruments that measure the solar wind and other particles, energetic ions, that sort of stuff. The UV imager is going to look at the atmosphere, try to determine its composition, whether there's things other than nitrogen and methane, for example, and how thick it is. We actually don't know what the actual thickness of the atmosphere is. We know it's thin, but we don't know how thin. We need to know that. Ralph, I didn't name these, don't blame me, is the color and infrared spectrometer. It's the same thing that Dawn has. And it'll measure the mineral composition and what the ices are and where they're distributed on the surface. We know they're there, but we don't really know what they correlate with, whether they're associated with impact craters or volcanoes, and we'll do that. And there are star trackers. The long-range imager is basically the high-resolution camera. It's a telescopic camera. That's what most people will see when New Horizons releases images, is those pictures. And this, of course, is the radioisotope generator, the hot box, the thing that generates the power. Dawn, if you remember, had those giant solar wings. Those were the solar panels. It gets its power from the sun. At this distance, the brightness of the sun looks like a 10-watt bulb. So it's not. There's no chance of getting any power from the sun. So we had to have the radioactive isotopes to generate power. So this is the system. Pluto, this is a double exposure, so that Pluto is much reduced in brightness, and then the outer moons, which are very small, are overexposed in order to show them. So there's Pluto, there's the large moon Charon, and then there's these 4 small moons orbiting at a large distance. We sort of expect to see additional moons. We don't know how many, we don't know exactly where. And there's actually observations which suggest that these bodies are tumbling. They're not rotating normally. They're sort of rotating in sort of odd sorts of ways. So they're interesting, but they're small. This is the encounter geometry. We're coming at it from here. It gives you a sense of what's going to happen. We're coming at it as a bullseye, going straight through the heart of the system. This is a close-up of that, showing the sequence of events. Again, coming from my side to the left side. We'll be passing through very close to the orbit of Charon. Charon will actually be on the opposite side from us. But right at closest approach, we're going to have to be taking a lot of pictures very quickly to capture all the objects at the same time. So we'll be imaging Pluto, and then Charon, and Pluto again, and then looking at the other ones, all in a very short, narrow window of time, because there's only one brief interval where we can get everybody at their best. And then as we exit the system, we'll be passing through the shadow of Pluto and then the shadow of Charon. And the reasons for that is that the occultations, is what they call them, are the best opportunities to look back and see the sun and the Earth eclipsed behind these bodies. And when we do that, you can actually use the ultraviolet and the radio instruments to actually measure directly the atmospheric density and the composition of the atmosphere. That's the best way to do that. So we designed the tour or the flyby to actually pass through those 2 points. We don't really expect much of an atmosphere on Charon, but we want to find out whether there's anything. We know there's one on Pluto. We need to know how dense it is, how heavy it is, and what it's composed of in order to understand the history. Just a couple more slides. This is a brief timeline of when things are going to happen. Again, the encounter's in July. We're right about here now. This is the approach phase. We're taking occasional images to monitor and begin the search for new objects. We probably won't see anything till about mid-May. That's the key point, is mid-May. That's when we start to exceed the Hubble resolution. So make that note in your calendar. There'll be big announcements about, oh, here's the new images that are as good as Hubble, and then we'll get better from then on. So that 2-month period is when things start to get interesting. Obviously, we'll be monitoring the system for other reasons, to make sure our trajectory is correct, because we're going to have to make adjustments to make sure we're at the price aim point. So we'll be monitoring for that. And also, we might see something that we didn't expect. So there'll be occasional releases, and we're almost to that point anyway. And then, of course, on departure, we'll be looking back, and we'll see a very narrow crescent, actually, as we depart. Now, let me see, do we have... No, okay, so I have to talk about here. The downlink of the data is actually very slow. You saw the size of the spacecraft, about the size of a grand piano. The antenna is actually a little bit smaller than that. That's very small. The Voyager antennas were actually larger than that. That means that, that it takes a couple hours to download a single image. And the plan is going to be to, in this time frame here, download key images so that we have a preserved record of what we saw and the key elements of the Pluto system immediately. And they're going to be compressed, so they're going to have JPEG artifacts. We don't know how severe it is, but be prepared. Some of the images are going to look a little not highest quality. But that's so that we have them on the ground immediately. We have something to work with, and we know what the encounter was like. Then in September or so, we're going to start downloading the entire image set in what we call browse format, which is also compressed, but not as badly compressed. So we'll have somewhat JPEG-y, but pretty good quality images of the entire data set over I forget what it is. I think it's, I want to say September through November, I think. And then in December, we start downloading all the images in full resolution, uncompressed format. And that takes into late 2016. It takes a better part of a year to download the entire data set intact, simply because the antenna is not that big. But in order to reduce the weight and get the fastest launch we could, it was necessary to keep the antenna size somewhat restricted. But in any case, we're going to do a lot of stuff. 6 months of encounter science, Hubble Space Telescope resolution 20 weeks out. Make composition maps, make temperature maps, measure the escape rate of the atmosphere, which is how fast the gas is escaping. Look at the atmospheric structure, look and see if either of those bodies are active, and a whole list of other things. And as the team likes to say, the most exciting discoveries are the ones that we don't anticipate. We don't know what we're going to see. It's a different body, one that we haven't seen before. We've never seen an icy satellite or an icy body not orbiting a planet before. All the other times have always been icy moons that have been orbiting giant planets, and that's a big difference. This is an example of some of the observations. There are a lot more observations, but this is just two, the ones that are probably of most interest to us because we like visual things. We're visually oriented. This is one mosaic that we're going to take. That's a 5x3 mosaic. It's on approach, I think about 3 hours out. And then at closest approach, we're going to do a scan. And these are individual images. And we're just going to just fire away. Just like a tourist taking a picture of a crime scene or something. But just fire away. I couldn't think of anything else to say. But anyway, those images are going to be better than 100 meters resolution, which is pretty good for a first-time exploration. In fact, it's darn good for first-time exploring. This is the dark side. So actually, we're going to see about that side. We're actually not going to see the North Pole. We're going to make an attempt to see the North Pole from the illumination of Charon. So basically, if you can visualize that, Charon's over here. It's reflecting light. Some of that's going to actually reflect back on Pluto. It's a long shot, and it's going to be very dim, probably going to be very noisy, but we're going to make the attempt anyway. So it's one of the many things we're going to try. Again, this is the timeline. This is when the encounter takes place, and this is the entire playback period. So it actually goes quite a distance, as I said, into 2016. What are we going to do after Pluto? One of the objectives, the original objectives, was to explore the Kuiper belt, and Pluto is obviously a member of that. It's one of the largest ones, but there are other objects too. And we've been conducting a search, and fortunately, with the assistance of the Hubble Space Telescope, we finally found two objects, small, less than 100 kilometers across, that are actually reachable in the flight path. And we'll reach those in early 2019. We'll visit one of them. And we're in the process of deciding which one we're going to visit. One of the reasons that this was so difficult, for those of you who are astronomers, is that this field of view from Earth is right in the middle of Sagittarius. So we're trying to find a very faint, small object in the densest star field that we have in the sky. So it's an exceptionally difficult task. And we finally had a call on the Hubble Space Telescope to help us out and do that, actually. And we finally found two objects that are reachable. So last two slides. We're almost there. This is where we are today. This is the orbit of Neptune, by the way. So we're actually cruising in at a high speed. We're going to pass by at 14 kilometers per second. Give or take a few. And I think this is the last one. This is one of the most recent shots we've taken. This is Pluto and Charon. There are a couple other exposures that they took where you can actually see the small moons as well. And you can view that on the New Horizons website. But we actually have the target in sight. There's only a couple pixels across, so we're not seeing anything. But stay tuned. We have a fun summer ahead. So thank you.